So we can now look at what we call half-life. What do we mean by half-life of a radioactive substance? And how can you carry out an experiment to determine the half-life of a radioactive substance? So let's look at half-life. What do you mean by half-life? Half-life simply means time. Half-life is the time taken for half of a radioactive sample to decay. The time taken for half of a radioactive sample to decay. So if I have a radioactive sample means maybe a certain mass of a radioactive element. Maybe I have 32 grams of a radioactive sample. What is a half of 32 grams? Is 16 grams. So I monitor the time. The time I can use a radioactive detector to find out the time taken for the radioactive sample to reduce from 32 grams to 16 grams. Why? Because 16 grams is a half of what? 32 grams. So the time taken is half-life. So half-life means the time taken for half of a radioactive sample to decay. As simple as that. Now, since we have said half-life is the time taken, time has so many units. Seconds, minutes, hours, days, weeks, months, years. So all these are units for half-life. So the half-life can be in any of these units. Now, how can you determine the half-life of a radioactive substance? So the first thing you do, experimentally, you get your radioactive sample, a radioactive sample of mass N0. We are saying N0 because we don't know the mass you may pick. You may pick 30 grams, another person is picking 100 grams, another one is picking 120 grams. So we are using just a general thing, that you get your radioactive sample, a radioactive sample of mass N0, sealed in, radioactive substances are very dangerous, so you have to seal them. Sealed in a container, is brought near a rate meter, or it is connected to a rate meter. A rate meter means this is now the instrument which is going to help you to determine how the mass of this thing is going to be reducing, how the mass is going to be decaying, what amount of mass. If you started with 62 grams or 64 grams, what will be the mass be after every 10 maybe minutes? You see? So the rate meter is going to help you. So you get a radioactive sample of a known mass. You get maybe 30 grams, you should know. Now the mass you have picked is what we call what? N0, the original what? Mass, before the thing decays. Seal it in a container, and then you bring it near a rate meter. Then after that, you now monitor the mass remaining, the mass which is left. With time, as time increases, the mass keeps on what? Reducing. So you read the mass and record the mass which is left. You see? After that, you now go and plot a graph, because you will be having so many masses. After 10 seconds, the mass is this. After 20, the mass is this. So what do you do with those masses and the time? You plot a graph. So a graph of mass against time is what? Plotted. And after plotting, you are going to get a curve. Your graph will be in the form of a curve, and that curve is called a decay curve. A decay curve is obtained. Now, with those masses and time, we said you plot a graph. How does a graph look like? Your graph looks like this. On the vertical axis, you have mass in grams. This is the original mass before the thing starts even what? Decaying. So when the time is 0, the original mass is already NO. This was the original mass. So here you have the mass on the vertical in grams. Then on the horizontal you have the time. The time could be in minutes depending on the time you're using, or hours. You see? Or days. So it is up to you depending on the time you are using. Are you monitoring in hours? Are you monitoring how the mass is reducing in seconds? So that is the time. And what we said, when you plot, you are going to get a curve. So your curve will look like this after plotting. Now, remember, when the time was 0, before this thing started what? Decaying. The original number was n0. This was the mass which you picked, the mass of the sample. So what you do, you now look for a half of this. From here up to here, where is the half? If I divide this by 2, it is around here. So if the original mass is n0, I now divide it by 2. You see? Getting a half means you divide by 2. So you get the original NO divided by 2. So a half of this space is around here. So this is original number divided by 2. Now, how do you determine a half-life? After getting a half of this as this part, you draw a horizontal line, which you will get, of course, on the graph paper, until it touches the curve. Then after that, you draw a vertical line, which is also, the line is already on the graph paper. Now, this line where it touches the time axis, you read this value, and that value becomes what? Half-life. You see, I've written T and a half. Half-life. We said half-life is the time. So I'm using this letter T and a half to represent half-life. So you read, this value you are going to get here is actually half-life. So after plotting the graph, we can put that in words, what I've just explained. You draw a horizontal line from half of the original mass, that is n0 over 2, is drawn to meet the curve. This is what I've just explained. After you have got a half of this, you see, a half of this space from here, see, from here up to here, a half is around here. You draw a horizontal line, this one. Then after horizontal line, you draw a vertical line. You see, that is the next statement now. The corresponding vertical line is drawn to meet the time axis. So the vertical line should touch, which is this one, until it touches the what? So the corresponding vertical line is drawn to meet the time axis. And the half-life, which is T and a half, is read on the time axis as shown in the graph. So if somebody gives you a question that describe an experiment to determine the half-life of a radioactive sample or substance and is giving you 5 marks, you can see where the marks are. You see, each time you mention important points, you get your marks. Now we have just talked about a graph, how to determine a half-life experimentally, and we said somewhere there that when you plot a graph, you end up with what? A decay curve. But somebody could also give you a question and says, the table below, like this one, shows the count rate. Now here the count rate is actually the mass. The mass recorded by a rate meter with the time. So maybe somebody was doing an experiment to determine the half-life of a certain radioactive sample, and he was using a rate meter. And these were the values, you see. Before the radioactive substance started decaying, that means the time is 0. The mass was already 64 grams. You see, this is the mass in grams, this is the time in days. And we say the time can be in hours, can be in days, can be in years, whatever. So you have two things, mass in grams and then the time in days. So when the time was 0, the mass was 64 grams. When the time was 24 days, the mass was 32 grams. 48 days, 16 grams, like that, until 120. Now, the person is saying, can you use these values to plot a graph and use that graph to determine what? Half-life. Plot a graph and use it to determine what? Half-life. Now, if you remember what we did, half-life is time. Whenever we are plotting the graphs for half-life, the time must be on the horizontal, while whatever is given, whatever is not a time, is on the vertical. Time must be horizontal. Then the other thing should be in what? Whatever you are given is, now in this case it is a mass, must be vertical. Now, for you to plot this graph, by there are two questions. After plotting graph, B says determine how long it would take 40 grams to remain. So let us see, how do you plot the graph? You look for the scale. Now, the convenient scales, the good scales, come from this 1, 2, 5, and 10. When you look at numbers from 1 up to 10, 1 is a good scale, 2 is good, 3 is not good, 4 is not good, 5 is good, 6 is not good, 7 is not good, 8 is not good, 9 is not good, 10 is good. So from 1 up to 10, these are the only good scales. Now, using these good scales, which I have put in the bracket, in what? In the form of a rectangle, in a box, you can also get other good scales out of them. How do you do that? You get these scales, these ones in the box, multiply them by 10. 1 times 10, you get 10. 2 times 10, you get what? You first multiply. You see this line? Multiplying by 10. 10 times 10, 100. 5 times 10, 50. 2 times 10, 20. 1 times 10 is 10. Or you multiply them by 100. If the values you are going to plot, they are in hundreds. If you multiply 1 by 100, 100. 2 by 100, 200. 5 by 100, 500. 10 by 100, 1000. If your values are in thousands. But the values may be as small as 0 point. What do? You can divide. Instead of multiplying by 10, you can divide by 10. 1 divided by 10, 0.1. 2 divided by 10, 0.2. 5 divided by 10, 0.5. 10 divided by 10, 1. Or you divide, instead of multiplying by 100, you can also divide by 100. And you get 0.01, 0.02, 0.05, and 0.1. These are good scales coming from the good scales, convenient scales. Now, out of these scales, we are supposed to use to plot the graph. Now, on the time axis, we have values up to 120. And you know a graph paper. I have here a graph paper. See? There's a graph paper here. So, on the horizontal, I start from 0. Remember, horizontal is what? Time. Time in days. What is the biggest time there? The biggest time here is 120. So if I use 20, 20, 20, 20, you see? I start from 0. Why? Because the time was 0. The first time, the smallest time is actually 0. So I can take every 10 small squares, I make it 20. So this is 20, this is 0, 20, 40, 60, 80. I keep on adding 20, 100, 120, 140. I continue. But why am I stopping at 140? Because my biggest value is 120. So I can only add 1. After all, my biggest value is here. Then on the mass, the biggest is what? 64. And the smallest is what? 2. So I can start from 0, below 2, up to 64. So I can take a good scale of 10. This is 0, you see, this is a 10, 20, 30, 40, 50, 60, 70. My highest value is 64. 64 is somewhere here. So using this scale, I can now plot. Plotting what? 0 and 64. 24 and 32. And to cut the long story short, if you are to do that, you end up with a curve which looks like this. You see, these are now the plotted points. This one is a plotted point, this is a plotted point, this is a plotted point, like this. Now you use a free hand. This is not a, if it was a straight line, you would use a what? A ruler to draw. But it's a curve, so you use a free hand, like this, to join. So each point you have plotted correctly, you get marks. Apart from that, they will also give you marks for mentioning, you see, labeling the axis, mass in grams. And then here you have time in what? In days. So they give you the marks for writing the title, a graph of mass against time. So if you do this from the graph, we are answering from the graph, the half-life is 24 days. How do you get 24 days? What was the original mass? The original mass was 64. What is a half of 64? 32. You see, 64 is somewhere here. 32 is somewhere here. So what you do, you draw a horizontal line where 32 is, then you draw a vertical line. And where the vertical line ends, you read that value. And that value becomes the half-life. The second question was, determine how long it would take 40 grams to remain. Where is the 40 grams? 40 grams is this one. So how do you know the time? You draw this line until it touches the graph. Then after that, you get another line which goes down. And then you read the value. And if you do that, you realize that the time is 16 days.